Okay, so good morning, everyone, or have a nice day to you, sir, and to my classmates. So, in this video, I will be going to discuss all about my report, which is all about the polynomial time reducibility. So, let's define first what is the so-called polynomial time reducibility. So, when we say polynomial time reducibility, that is a concept in computational complexity theory wherein used to compare the difficulty of computational problems. And that is a formal way to show that solving one problem can be transformed into solving another problem within a polynomial time. So that means to say that in reducibility, that is a tool that we use to compare the difficulty of such computational problems. So that also formalize, I mean, the idea of one problem into another, or in such a way that solving the second problem or another problem also solves the first before you go sequentially. So, for example, if we have here a situation, let me see. If a problem A is if a problem A is said to be polynomial time reducible to another problem B and written as A um, less than or equals to B, and A is that is the so-called A, that sign is also signifies that A is polynomial time reducible to B. So that means to say that this if there exists a polynomial time algorithm that also transforms any instance of A into an instance of B, and such that the answer for A can be derived from the answer for B. So it will also matter if it can be solved, if that will be solvable into A. So that will also confirm that into your B, it will be solved as well. So if A is less than or equals to the polynomial, the P of B, then solving B is at least as hard as solving A. So assuming that the polynomial time solution, so that is a common notation in computational complexity theory, that A is less than to or equals to P of B. Now, where A and B are decision problems or the languages. So the subscript P right there, that indicates that the reduction must be done in polynomial time. And that implies that if B is solvable in polynomial time, then it is also solvable, then A is also solvable in polynomial time. So in that one, problem A is said to be polynomial time reducible to problem B. That is denoted as that um, symbol, or I mean that formula. If there is a polynomial time algorithm that transform any instance of that A, will also um, be advisable or useful into B. The solution for A can be derived from the solutions to of B as well. So next, this concept is a fundamental in classifying problems in complexity, such as P. There is also NP, and there is also NP complete. So when we say P, that signifies as a polynomial time that is consisting of problems that can be solved by a deterministic algorithm and polynomial time. These are considered easy or efficiently solvable problems. So um, that is definitely easy to solve, since from the word determine. So in polynomial time reducibility, it helps us to classify problems into different complexity, and that classes or group based actually on their difficulty and the time it will takes to solve them. So say for example, if in your A, if it is easy to solve, so and there will be a determined answer for that instance. So therefore, in to your B, it will be the same thing, the same manner. So that classification will also signify in the polynomial time since everything was deterministic. And if it's non-deterministic, so therefore that will be into the non-deterministic polynomial time later on. I will also discuss that one. So it refers to solvable by deterministic algorithms in polynomial time when we say the problems in P are considered easy or efficiently solvable since there will be a solutions can be computed within a reasonable amount of time, and as the input size grows, it will be easy for us to determine the answer therefore. Now let's move on to the non-deterministic polynomial time. Into the non-deterministic polynomial time, this class um second error here. So this class consists of problems for um, which a solution can be verified in polynomial time, even if finding the solution might not necessarily be efficient. Um, so in the non-deterministic polynomial time, that consists of problems for which a given solution can be verified in a polynomial time manner, even if finding that solution might not be efficient or possible in polynomial time. So for verification, the key idea there, verification of a solution is easy, that is in polynomial time. So finding the solution may require significant time, potentially, or non-polynomial. And say, for example, in the Sudoku problem, if someone gives you a completed Sudoku puzzle, so you can quickly verify that it's correct. However, solving a large Sudoku puzzle from scratch might take a long time, diba? So that's why, in summary for that one, the non-deterministic polynomial time focuses on problem wherein we are checking the solutions is fast, but solving them might be difficult. So the one of the example as well, the traveling salesman problem asks if there is a tour of certain cities with a total distance below a given threshold. Checking a proposed solution is easy, but finding one may not be. So that's actually how does it work in non-deterministic polynomial time. So it's different by deterministic because it's really easy to solve such manner wherein there is already a solutions from that, and by applying or by using that into a reality, therefore it's easy for you to break down everything. But here in non-deterministic polynomial time, you do have such idea. However, by applying that into a real norm, so it will be um hard to solve that certain situation. So let's actually also try to check the next. So we also do have, as what I mentioned earlier, that we also do have the um non NP complete. So let me click next. Excuse me. So the NP complete, these are the hardest problem in NP. A problem C is NP complete if it is in NP. Every problem in NP can be reduced to C in polynomial time, where in A less than or equal to P or C. So that means to say that the NP complete problems are, this is actually a special class of problems in computational complexity. They are the hardest numbers, problems within the class of non-deterministic um, polynomial time. So meaning they are both difficult to solve and critical for understanding the structures of non-deterministic. So say for example, the solutions for that one is really hard. So therefore, since as hard as the solutions to get, so in by applying that into the reality, it will be also the same thing. It's hard to solve them. So if It is in NP. The problem C belongs to the class non-deterministic, meaning its solutions can be verified in polynomial time. So if that certain solution is cannot solvable, so therefore by applying that one, it's not solvable either, diba? Now, if you find a polynomial time algorithm to solve a NP-complete problem, all problems in non-deterministic can also be solved in polynomial time. This would imply that P, your deterministic is equals to non-deterministic, solving a fundamental question in our course actually. Now, there will be an example for non-complete problems. So say, for example, in the traveling salesman problem, can a salesperson visit a set of cities exactly once and return to the starting point with a total cost below a given value? So um it will be a ano na siya, there will be it's actually hard to prove that a salesperson can visit exactly once. So a salesperson must visit a set of cities exactly once, starting and ending at the same city, while minimizing the total travel cost. This you also do have the distance, the time, and word expense. So the decision version of that one, that given the time or the total cost threshold, if it will matter with the time as well. Is there a tour? Is there a path that we can visit the city? Then if from that certain city, then we'll end into that place as well. So it will be like hard for us to really solve that matter. So if A can be reduced to B, another example for that, if A can be reduced to B and B is in P, then A must also be in P. That's actually the what do you call this one? Um, mm, that's the approach all about. So if an NP complete problem can be solved in polynomial time, then all of the problems in non NP and non-deterministic polynomial can be solved in polynomial time as well. So since all non-deterministic complete problems are interrelated via polynomial time reductions, so proving that one non-deterministic complete problem can be solved efficiently would also imply that every problem in that non-deterministic can also be solved efficiently. Now, so we also do have here for polynomial time reduction, I actually have here a set of example, basic examples. So even number problem reducing to the divisible by two problem. So a problem one, even number problem. We also have here I call this a number for the input. We have the situation a number n for the input. And for question, is n an even number? And the situation two for the problem two, divisible by two problem. So the input there will be a number n, and the question is n divisible by two? So we'll see that later on. What does it signify all about? By the way. Now let's move on to the reduction. To solve the even number problem using um, the divisible by two problem. So first we can do so with the input n into the divisible by two problem. If the output is yes, return yes for the even number problem. If the output is no, so return no for the even number problem. So actually, um, that example, we are going to solve the even number problem using the divisible by two problem. So we want to determine whether, for example, n is equals to 8. That is an even number, right? So when our input is n is equals to 8, the question's right there, is it divisible by 2? So, yes, di ba? 8 is really divisible by 2 since 8, the modulus for that one or the remainder is equals to 0, di ba? So since the output for the divisible by 2 problem is yes, so we conclude that our n is equals to 8 is indeed an even number. So therefore, it's deterministic. It's really easy to really solve that one. So we also do have another situation. Say, for example, your input m will be is equals to 7. So into the divisible by 2 problem. So the questions there is your 7 divisible by 2. So if you will check that one with the modulus or with a remainder of that, if using that n, that 7, the answer will be no, since 7 is not divisible by 2, since 7 will also have the modulus or remainder of 1, di ba? Since the output for divisible by 2 problem is no, we can conclude that therefore n is equals to 7 is not an even number. Then that shows how the even number problem is solved, reducing it into the divisible by 2 problem using that simple logic and constant time computation. So that is really simple. So in time reducibility, I mean in the polynomial time reducibility, if it is a what we call this one deterministic, if that question or that input, if it will be solvable into that given problem, given situation, if it can produce the logic or can solve the logic. So basically, it is deterministic and it's really easy. So anyway, um, this reduction is a trivial because checking if a number is divisible by 2 already answers whether it is even. So the transformation for that involves no computation other than passing n, diba? Which is clearly polynomial constant time in this case. So a simple example of polynomial time reducibility that also proved that deterministic is really easy to solve. So anyway, that is my report all about. So why is this a polynomial time? Just to also prove that one. So it is a polynomial time. The transformation from one problem to the other takes constant time. So it's really easy. The reduction is a single step that also ensures that the answer for problem one is the same as the answer for problem two. So this that's demonstration demonstrate also the concept of polynomial time reducibility, wherein straightforward way. And as what I mentioned earlier, the problem of problem A, even number, is reduced to problem B as well. So it's divisible by 2, diba? And therefore, um, since that is inconstant, so therefore it is considered as a polynomial time. So thank you so much, and I do hope that it's um what I mean. I hope so that you really understand what is polynomial time reducibility all about. And that's it for my report. Thank you so much, classmates and sir. Have a nice day.